So particles outside the nucleus, suppose this is the nucleus of the atom. Famous hadrons are protons and neutrons. They are called the hadrons. They are under the influence of the strong force, and the range of the strong force we have done is equal to the diameter of the nucleus. Now, particles outside the nucleus, inside the atom, outside the nucleus, they are called leptons. Leptons are considered fundamental particles, basic particles. They are fundamental particles. I mean, they have no further division. Protons, neutrons are not fundamental particles because they have division. They are made up of quarks, but the leptons are considered basic particle, fundamental particle, because their division is not possible. And the famous leptons are, number one is the electron. Number two is neutrino. Number three is tau, and so on. There are many more. So we have to discuss here only electron and neutrino. They are very light particle. Their masses are very small as compared to the hadrons. Now, each particle has its antiparticle, like electron has its antiparticle, which is called positron. Electron is represented by the symbol e minus 1, 0, or it is also beta, because the fast moving electron is called the beta. And the antiparticle is positive electron, either this or we can write plus 1, 0. And similarly, the neutrino has its antiparticle, antineutrino. The symbol for the neutrino is this, and the symbol for the antineutrino is this additional dash sign. Now, they are under the influence of the weak force, and the range of this weak force is 10 power minus 9 meter or 10 power minus 10 meter. So outside the nucleus, there are leptons. Inside the nucleus, there are hadrons. Hadrons are under the effect of the strong force, and the leptons are under the effect of the weak force. Leptons are fundamental particles because there is no further division. They are considered basic fundamental particles. Each particle had its antiparticle, electron, positron, neutrino, antineutrino. Now suppose during a nuclear reaction, when neutron is converted into proton, neutron, no charge, mass is 1, plus 1 charge, mass is 1. Along with this, beta particle is emitted. And along with the beta, antineutrino is emitted. So we have to remember this reaction. Neutron is converted into proton. Beta particle is emitted, antineutrino is emitted. So instead of this beta, you can also write electron. So neutron and the protons are hadrons, but these two particles are leptons. Neutron has the composition 1 up and 2 down quark. Proton has composition up, up, and down. It means when a neutron is converted into proton, one of the down quark is converted into up along with the emission of the beta particle and antineutrino. And this is weak interactive reaction. So weak reaction, weak interactive force is involved here. But in this reaction, charges are conserved, masses are conserved, momentum is conserved, mass energy relation is conserved. Look, the total charge here is 0, and here plus 1 minus 1 and 0 total becomes 0. Now come to the mass total is 1. So 1 and 0 and 0, it's 1. So momentum conserved, charges conserved, mass conserved, mass energy relation also conserved. Now similarly, when proton is converted into neutron, positron is emitted and neutrino. Look, here in the first, this electron is emitted, here the positron emitted. Here antineutrino, here neutrino. So when neutron converted into neutron converted into proton, electron and antineutrino. But when proton converted into neutron, positron and neutrino. So here electron, and here it's antiparticle, here antiparticle, antineutrino, and here particle itself, neutrino. Now this P has 1, 1 and 0, 1. So the charge is 1, charge is 1 here, 0. So the charges are conserved, masses are conserved. So whole reaction is conserved, mean in terms of the masses, in terms of the charges, in terms of the momentum, in terms of the mass energy conversion, it is conserved. Now look at the composition. Proton has 2 up, 1 down quark. Neutron, 1 up and 2 down quark. Now when proton is converted into neutron, 1 up quark is converted into down along with the emission of the positron and neutrino. So these two reactions are very, very important for the atom. Okay, now when particle interact with its antiparticle, like electron interacts with positive electron, positron, then the whole mass, mean the mass of the both particle and antiparticle, is converted into energy. And 2 gamma rays photons are emitted. And the relation, look, energy is equal to mc square. So the masses are converted into energies, and the energy is in the form of gamma rays. So the masses are converted into energy, mean when particle interacts with its own antiparticle, whole of the mass is converted into energy according to famous Einstein equation E is equal to mc square, and the energy will be in the form of gamma radiation. Now for this reaction, no momentum, mean mv, is required. No kinetic energy required to interact with each other. So if the initial momentum is 0, then the final momentum also 0. That's why the both gamma rays photons are traveling with the same momentum but in the opposite direction. So this is plus mv and this is minus mv. But do remember, gamma rays photons, no mass. So we can't write mv and mv. The momentum of the photon is equal to h divided by lambda. So instead of the mv, we will write h over lambda positive, and here minus h. Momentum is a vector. This is positive, this is negative, equal. So the total momentum, the sum becomes this h over lambda minus h over lambda, it becomes 0. So the law of conservation of the momentum is valid here. Okay, now suppose we have this atom or the nucleus. This Z is representing proton number in the nucleus, and A is representing the mass number, mean the number of protons plus number of the neutrons. Now, if in any nucleus, in any atom, this Z is greater than or equal to 83, or the mass number greater than or equal to 200, then the nucleus, the atom, is called unstable. But this is natural unstable, not artificial. Natural unstable. Now, this natural unstable will emit radiation to gain stability, and this is called radioactivity. Okay, so if the proton number is greater than 83, mass number greater than 200, then the nucleus is called natural unstable. It emits radiations to gain stability. So the emission of the radiation from any unstable nucleus, this is called radioactivity. And this process is called radioactive decay. So when radiation emitted, for example, uranium is naturally unstable, it is emitting alpha, so it is converted into thorium. Mean after the emission of the radiation, number of the uranium nuclei are decreasing and the thorium increasing. So this decrease in the number of parent radioactive nuclei after emitting radiation is called decay. So the uranium is decreasing in number because it is emitting alpha, so it is converted into thorium. Similarly, when uranium emits beta, it is converted into neptunium. So this decrease in the number of the parent nuclei, mean the uranium, natural radioactive nuclei, after emitting the radiation is called decay. It is represented by either Dn or delta N. Now, what is decay? The decay is decrease in the number of the parent radioactive nuclei after emitting radiation is called decay. And this decay process, this radioactive process, number one, is random. And number two, it is spontaneous. Now, the random mean no one can predict which nucleus will decay next. Mean which nucleus will emit radiation next time. No one can inform about it. And number two, no one can predict how many radiations will be emitted. Mean what is the number of the radiation? No guess. Number three, what will be the time of emission? And number four, what will be the direction of emission? Direction of motion of the emitted radiation. So this is random in terms of the number, in terms of the time, and in terms of the direction. So this is totally random behavior because no one can predict which nucleus will decay next, how many radiations will be emitted, what will be the time of the emission, and what will be the direction of the emitted radiation. This is random. And come to this spontaneous. Spontaneous mean the rate of decay is not affected by surrounding physical conditions. Mean the rate of emission, mean the number of radiations emitted per unit time. How many radiations will be emitted in 1 second in unit time? That is not affected by any surrounding physical conditions like the change of the temperature of the atmosphere, and number two, like the change of the pressure of the surrounding. Mean high pressure, low pressure, mean variation of the pressure has no effect on the number of the radiations emitted. Change of the pressure has no effect on the rate of emission. So it is totally spontaneous. We can't say that hot sample, high temperature sample will emit more radiation and the low temperature will emit less radiation. No, no effect of the temperature. If both samples of the same size from the same element, so definitely they will emit the same number of the radiation. So the rate of emission of radiation is not affected by surrounding physical condition. Mean by increasing the temperature, we can't change the number of radiation emitted per unit time. Now suppose x-axis is the time, y-axis has a count rate, and this is the trend of the decay. To show the random behavior, we have to put kink on the line. So the bend of the kinks on the line is showing the random behavior. And for the spontaneous, if this is the time, this is the count rate, and if this is the trend of the hot sample of the uranium, then definitely this will be for the cold as well. So no effect on the rate of emission. So hot and cold sample of the uranium of any radioactive nucleus will have the same trend, same graph. But when we have to show the random behavior, we have to put these kinks on the graph. So kinks are showing the random behavior. Now, the rate of decay mean decrease in number of radioactive nuclei per unit time after emitting radiation is called the rate of decay, and it is represented by dN over dt, and it is also known as activity. So activity is represented by A. So A activity means dN over dt. How many numbers are decreasing per unit time? And this activity is measured in unit Becquerel, capital B with small q. If one nucleus is decreasing in 1 second, then the activity of this sample is 1 Becquerel. So the number of the radioactive nuclei decreasing per unit time, this is the activity, and it is measured in Becquerel. So 1 Becquerel activity mean one nucleus is decreasing in 1 second.